Hello, this is me, Max, or the Technomancer, here doing a mod tutorial on psi vectors. So I'm going to expect you already know the mod psi very well, except for the point of how vectors work. So vectors are pretty key to the mod for the more interesting things you can do with psi, and a lot of people get rather confused by them. So this video is going to try to teach you vectors as if you know nothing about vectors already, but I'm not going to teach you all sorts of stuff about vectors. I'm only going to teach you the stuff about vectors as it relates to psi. So there's all sorts of things you can do with vectors in real mathematics that aren't really used in psi because you don't need them, so I'm not going to talk about them. So I'm going to try to keep this pretty simple. First off, what is a vector? Well, generally a vector is a bunch of numbers that you work with together. For example, if I take a vector ruler, it shows a vector here, which is inside that square brackets, 3 numbers separated by commas. There. Right. So I've got this in relative mode now, and if I just look, I've got 3 numbers. Now, a vector in reality can have any number of numbers in there, any amount of numbers in there as you want. You could have a vector with 2 numbers, you could have a vector with 15 numbers, but in psi, all the vectors have 3 numbers. Okay? So what is a vector? Exactly, besides just a collection of numbers. What is the idea of this? Well, vectors is about relative to. So, let's pretend that you're looking at some sort of chart, some sort of graph, and this spruce wood log is your 0, 0, your origin on the graph. Well, this point over here, how would you say it is? Actually, let me make sure I'm working in the correct. Let's do with positives right now. So over here, you'd say this is, from your origin, this is about positive 3, because it's 3 on the x from the origin and 3 on the z. Well, if I do that, that's exactly what it is. 3, 0, 3. That 0 in the middle is y, because with 2 numbers, we'd just be talking about the x and y coordinate. Sorry, x and z coordinate. But with 3 numbers, we've also got the y coordinate. So a vector is, simply put, a set of coordinates. Now, I can talk about coordinates relative to a block, or I can talk about coordinates relative to 0, 0 of the world. So, usually you think of vectors as a point. A point in the world defined by these numbers, like this block right here. And in psi, there are 2 ways to think of vectors, and one of them is as a point. Now, when you think of vectors as a point in the world, it's relative to world 0, 0, 0, not relative to this block over here, relative to, if I were to TP to 0, 0, 0, that, right? And that's literally just your Minecraft coordinates, your x, your y, and your z. So if I shift right click with this, I get that, correct? Pretty simple. So right now I'm using vectors as coordinates in the world. Now if I make them relative to this block, it's like a direction, because if I'm standing on this block and looking at the block that the vector designates, that's a direction. And no matter where I'm standing, that direction is the same. So if the block under my feet was my origin, then looking at 3, 3, 3 is exactly where I'm looking right now. So if you look, so you can think of it as a direction or a point, right? So when you think of it as a direction, think of it as like a giant arrow pointing that way, right? So it's this big, very badly, clumsily built arrow, I must say, pointing over there, saying, okay, this is direction. So you might use that for what direction is the player looking? Well, with absolutely these coordinates, where is the player? Now, I'm guessing that right now it sounds pretty vague what I've just said, but it'll make more sense in a bit. But I should probably talk about magnitude, because it's pretty important to understanding vectors. So I've got a vector construct here that just lets you build a vector from some numbers. So I've got a vector where the x is 3, my y is 4, and my z is 0. Okay, pretty simple. So if I've got it set back to magnitude right now. And I'm putting it into this operator, vector magnitude, which turns a vector into a number. What is it doing exactly? It's going to print it out in debug. Well, let's pretend starting from 0, 0 to that point in the 3, 4. So if I just tear down this, there. I misclicked. Hold on. Oh no, actually, it's in the wrong spot. Oh, that's even worse. There we go. 3, 4. How long, hopefully you remember a bit of geometry class, how long is that line? If I were to draw a straight line from the center of this block to the center of this block, how long is that line? That's basically what the magnitude is. That's exactly what the magnitude is. So if you don't know the equation or you've just forgotten it, the length of a line in three-dimensional space is how far is it on the x-axis squared, plus the length on the y-axis squared, plus the length on the z-axis squared, and then the square root of all of that. So in this case, that would be 4 squared plus 3 squared plus 0 squared, and the square root of all of that. So that comes out to the square root of 25, which is 5. So the magnitude should be 5. And as we can see, there it is, magnitude 5. Which means the magnitude is just how long is the vector. Okay, that's pretty simple. It's a pretty simple concept, but pretty important. Now, let's talk about something a little slightly more complicated. I don't think I actually said it well. If I make a vector, if I negate a vector, actually let's talk about negate sounds like a good thing to start with. It's pretty simple. It's pretty simple. So let me just set up the spell here. I forgot to set this up beforehand. Hold on. Okay, so I've set up a negate spell here, and it's pretty simple. It's got this vector that I've created, which has which is a 3 on the x and 4 on the z. And it's putting it into this vector negate piece, which I'm going to explain very soon, which outputs a vector, and I'm splitting that up. So extract the x, so just give me the x coordinate of the vector as a number, extract the y, and extract the z, and basically print those all out in order. So tell me the x, then the y, then the z. So what negate does is actually very, very simple. I put in 3, 0, 4, and it gives out -3, 0, -4. It basically multiplies the whole vector by -1. It's that simple. What it's doing is it basically gives you a vector that's the same magnitude, so the same distance, going the exact opposite direction. So over here instead of over here, for example. Pretty simple. And also, this same spell I'll use to show off vector multiply, which is pretty simple as you might imagine. So, oh, that is multiply. I meant vector multiply. So vector and number. And this is, as you're going to imagine, just going to multiply every part of it by 4. So multiply 3 by 4, multiply 4 by 4, 0 by 4, but that doesn't matter. See? So it just multiplies the whole vector. And as you'd imagine, there's also vector divide and vector subtract. And vector subtract is a bit special. So there's also vector divide, and that acts as you'd imagine. So there's also vector sum and vector subtract, which I'm not going to show, but they're basically the same sort of thing, but they take multiple vectors. So add the two A's together, add the two B's together, add the two C's together, and give you a new vector that is the sum of all those parts. So the new vector the new vector's x coordinate is the first two vectors x coordinate put together, and so on. And subtract is the opposite, as you'd imagine. So far we've been doing pretty simple stuff with vectors. Now, the next thing is, well, it had to come eventually, cross product and dot product. And, well, they're pretty complicated. They are very complicated, really, but let's try and do this best we can. So I think I'll start with let's see here, which one should I start with? Hold on, let me decide. Let's do dot product, because compared to it's actually pretty simple, just not compared to the cross product. What it really does is it turns two vectors into a number. So let's go back to that vector multiply, except a bit different. It's like a vector multiply, but a bit different. So we put in our two vectors, and this vector has an x-coordinate of 5, and this one has an x-coordinate of 4. We multiply 5 times 4, that's 20. 20 plus 3 times 2, the two y-coordinates are actually, equals 26. And then 0 plus 0 times 0, the two z-coordinates equals 0, so 26. And this spell outputs 26. So dot product's pretty simple. The really nasty one is cross product, because this one isn't a simple relationship. It's not, oh, multiply it all by 3 or something like that. This is pretty complicated. And the uses for this are a bit limited, but I'll try my best to explain it. The cross product is where you have to think of these vectors as directions. There's no two ways about it. Think of them as directions, or you're going to have trouble. So let's take this vector. Now, this spell I tried to make very, very simple. The simplest cross product I could think of. The first vector has 1 on the x and 0 on everything else, and the second vector has 1 on the y and 0 on everything else. And this outputs a vector that's 1 on the z. So what's happening exactly? Well, what exactly is happening is this is our little x vector, and that is our y vector. I'll use a different block to designate the endpoints. Now, it's a known fact that it takes 3 points to designate a plane. That's just a geometrical thing. If you have three-dimensional space and absolutely any orientation is possible of things, well, if I make 2 points if I make one, now try and work out what flat surface these points represent. 1 point, it could be absolutely anything. That point could be part of a plane of any rotation in the universe. 2 points, infinite rotations are possible, because there's a line between them. You've made a line with your 2 points, but this line could be on infinite rotations of planes. You're limited to one axis of rotation. This is kind of complicated. It's really complicated. Basically, take my word for it, 3 points designate a plane unless they're all in a line. Okay? So if I've got 3 oak wood in random positions, you can work out a plane from this. Where is our flat surface? Well, this is our flat surface that you have to imagine just goes on forever. Right? Now, and I can be a little more complicated, though. This will be painful to build very soon. If I do this is supposed to be Cerise, then your plane is something like this. This is your plane that you're working with, your flat surface. It's Minecraft, it doesn't look very good. Okay, so vector cross product takes very heavy advantage of this plane. So, what's the plane in this case? Where the origin is 1 point and the endpoints of your 2 other vectors, if you think of them as points, are 2 other points on this plane. Well, this is your plane. Pretty simple. Now, here's where it gets weird. The cross product gives out a vector where the direction is perpendicular to the plane from the origin. So it could give out here or here. So it has to work out something that's perpendicular to your plane from the origin. Now, a few things I should mention right now. An important exception. If all 3 points in the plane are in a line, there are infinite possible planes that could be formed from this. I could have this be a plane, that works, or this could be a plane, and so on and so forth. Diagonals and everything. So in that case, it outputs 0, 0, 0. Your cross product will be, no, it'll be the origin. That will be your cross product's output, if they're all in a line. Otherwise, it's this. So you might be wondering, there's two details you haven't pointed out, Max. Well, one of them is, there's two possible perpendicular lines. It could go that way or that way, right? Both are perpendicular from the origin. So they're both valid, and obviously a piece can't output two different things at once. So there is a way that it determines which one. Basically, you noticed how it outputted z of 1. That would have been this case. It outputted this case. So negative 1 is also valid. It's this way. So what does it take for it to output negative 1? That's dot product. Literally, swap the order you input them. Now it's negative 1. So it determines which direction to make the new vector be based on the order you input the first two vectors. So that's part of it. I'm not going to get into the exact details there. If you really find a need for cross product, you can do it experimentally. It's a complicated procedure. Now the other thing is, what is the magnitude of the vector? And by that I mean, well, this is perpendicular to this plane, but so is this. So which one is it? Well, I should fix that. If I just demonstrate, now you'll notice that the magnitude of the vector, when both of the inputs' magnitudes were 1, the magnitude of the new vector was 1. And there is a reason for that. It's not always going to be 1. The magnitude depends on the magnitudes you put in. So if this one has a magnitude of 3, the output has a magnitude of 3. And if this one has a magnitude of 2, so now one has a magnitude of 3 and the other has a magnitude of 2, the output has a magnitude of 6. Literally, the magnitude of your new output vector is the magnitude of the two input vectors multiplied together. It's that simple. So if this one's 2 away and this one is 3 away, then your output is going to be 6 away. That is cross product in a nutshell. And it is a very odd operator. There are plenty of uses for it in real world, not so many in Psi, but yeah, that's cross product. Now, there is one piece that I'm not, one important vector piece that I'm not really going to get to today. Wait, did I cover normalize? Did I cover normalize? That was that's pretty, I didn't cover normalize, my bad. Ooh. Hold on, before I transfer on, I need to do normalize. I forgot normalize, it's pretty important. So, I can use this one actually. I can use this. So instead of this, I'll just use normalize. What normalize does is it changes the vector so that it's the same exact direction. So it starts here and it goes this way. Well, this one has a magnitude of what, like 3 or something, 3 point something. So it changes it so it's the exact same direction, but it has a magnitude of exactly 1. Which really means it's sort of like this pixel here-ish, because diagonals are weird. So this is the same direction as, this number gets ignored, as a 3, 4 vector, but it just has a magnitude of 1 instead of 5. That's what negate does. Sorry, normalize does. So it's pretty important, very useful for things. Now there is one operator, I was trying to say this earlier before I remembered normalize, that I'm going to not talk about, and that is vector project. I'm going to be honest here, I don't actually know how this works. It's complicated. I mean, I can show you the equation. There is an equation that determines the output of this, and it is complicated. It is very complicated. It involves trigonometry, and I don't know how to put vector project in simple terms. I I'm not even going to try to explain what it does, but it is hard to explain what it does. It really just is very hard to explain what it does. I can't even show you the equation properly because it involves characters I can't type into this window. So if you really want to know what vector project does, I'll link you to a Wikipedia article that explains in detail everything you need to know about vector project, but I'm guessing you'll walk away from that having no idea what you just read, because it is complicated. It doesn't make much logical sense, and it is strange. So sorry about if you really were here to learn about vector project, I'll put a Wikipedia article link in the description. So goodbye.